be discussing an important chapter from algebra, that is theory of equations. So before, let's begin with the simple definitions. So first we have real polynomial. So if I have f of x is equal to a naught plus a1x plus a2x square, so on, where all a's and x are real numbers. So when all the a's and x in a particular polynomial, if they are real number, then it is called a real polynomial. Similarly, we have complex polynomial. So again, it is same f of x, where all a's and x's are complex numbers. It's simple. When all the a's and x's are real numbers, then it is real polynomial. And if they're complex, then it is complex polynomial. Then we have rational expression. See, when I say a number is a rational number, for a rational number, it should be of the form p by q, where p and q are real numbers. So similarly, when I say a rational expression, it has to be of the form p by x and by q by x, where p of x and q of x are polynomials. Okay, so when we have p of x by q of x, where p of x and q of x are both polynomials, then it is a rational expression. Next is degree of polynomial. So if we have a naught plus a1x plus a2x square, so on till an x power n, then n is the degree of this polynomial. So basically, the highest power of x in a particular polynomial expression is called the degree of polynomial. So in this case, my a's and x's can be either real or complex. So there is no issue on they being real or complex. But what we are concerned is just the highest power of x. So whatever is the highest power of x, that becomes my degree of polynomial. In case if I have n is equal to 2, so then we call it as a quadratic polynomial. Then it is a quadratic polynomial. When n is equal to 3, then it is cubic polynomial. Okay, so because when n is equal to 3, my polynomial will be of the form a3 x power n plus a2 x square plus a1x plus a0. Okay, so this becomes my cubic polynomial. Of course, I'm just writing the other reverse side. The a0, a1x, a2x square is here. I'm just writing the highest degree term or the highest power of x term first, and then reducing it. So similarly, my quadratic polynomial will be something like a2x square plus a1x plus a0. Okay, so it will be of this form. Okay, then we have the next definition, that is a polynomial equation. See, when I say f of x is equal to say a2x square plus a1x plus a0, then this becomes a quadratic polynomial. But when this particular quadratic polynomial expression, when it gets equal to some value, say 0 or some other value, then it becomes an equation. So whenever we have f of x is equal to 0, then where f of x is a polynomial, then this f of x is equal to 0 becomes a equation. As such, if we have only f of x, then we call it as a expression. But when it is equal to 0 or some constant value, then we call it as equation because there is equal to some value. Okay. Then we have, let's go a little. Okay. Yeah. Roots of equation. So the values of variable x satisfying the given equation are called the roots. So suppose I have f of x is equal to 0 is a equation. Say, let me take a cubic equation for simplicity. A2x square plus a1x plus a0 is equal to 0. So this particular quadratic equation will be satisfied for some value of variable x. So for example, f of alpha satisfies this equation. So I will have f of alpha is equal to a2 alpha square plus a1 alpha plus a0 is equal to 0. So that means alpha is a root of this equation. So whenever some value of the variable x satisfies this particular equation, f of x is equal to 0, then we say that particular value is the root of the equation. Okay, so the next definition we have is solution set. So solution set is nothing but the set of all the roots of an equation. Say, again, let me take a simple example. Say I have my f of x is equal to x square minus 3x plus 2 is equal to 0. Okay, so my f of x is equal to 0. So because it is equal to 0, it's an equation. Now, what are the roots of this particular equation? This particular equation I can rewrite as, if I factorize it, this will give me x minus 2 multiplied with x minus 1 is equal to 0. That means, of course, I hope you have already studied this in your class. You have how to factorize a quadratic equation. So that's how I'm factorizing it, and I'm getting this particular equation. So this implies my x is equal to 1 or 2. So my solution set is 1 and 2. So the set of values of x for which the particular equation holds true, then those values of set x or the variable is called the solution set. Okay. So I hope the simple definitions are clear. So let's do a simple question to begin. Let's copy it here. Okay, there is some problem. Let's copy it again. Again, some issue. So what it says, if x is equal to 1 and x is equal to 2 are solutions of the equation x cube plus ax square plus bx plus c is equal to 0. So he has given us an equation and he's saying that x is equal to 1 and x is equal to 2 are the solution of this equation, and a plus b is equal to 1. Then find the value of b. So basically he has given an equation f of x is equal to x cube plus ax square plus bx plus c is equal to 0. So this is the given equation. And he has also given us a condition that a plus b is equal to 1. And he has told that x is equal to 1 and x is equal to 2 are solutions of this equation. So what does it mean? I can write f of 1 is equal to 1 cube plus a1 square plus b1 plus c is equal to 0, which is nothing but a plus b plus c is equal to minus 1. Yes, so this is my first condition which I have in terms of a and b. Now he has also told us that f of x is equal to 2 is also a solution of this equation. So again, instead of x, we can replace the x with 2. We will get 2 cube plus a multiplied with 2 square plus b multiplied with 2 plus c is equal to 0. So this will give me, I'm taking this 2 cube, that is 8 on the other side, and writing the remaining terms. So 2 square is 4a, 2 square is 4. So I'm writing plus 2b plus c is equal to minus 8. Okay, so this is my second condition. And he has already given us one condition that a plus b is equal to 1. So this is the third condition. So in this particular problem, we have 3 equations, that is 1, 2, and 3, and we have 3 unknowns. So depending on how many number of unknowns we have, we need so many equations to get the unknowns. Now suppose if I have only one unknown, so and I have an equation like this, say 2x plus 1 is equal to 0. So because in this equation there is only one unknown, so one equation is sufficient for me to solve for this one unknown. Okay, so this will give me x is equal to minus half. Now if I have, say, equation like 2x plus 3y plus 1 is equal to 0. So this is an equation which has two unknowns. So I cannot solve this equation no, just like that. I need another equation with these two same unknowns so that I can solve them. So again, if I have, say, x plus y is equal to some value, say plus 2 is equal to 0. So now I have, this is equation 1, this is equation 2. So with the help of two equations, I can solve for x and y, that are two unknowns. So in this question, we have three unknowns, a, b, and c. So to solve three unknowns, we will need at least three equations. So that's how we are now having three conditions in A and B, or three equations in A and B. We can use that to solve for A, B, and C. Anyway, we just need, I think, B, find the value of B. Okay, so we can do by multiple ways this solving of equations, but let's take a simple method. Now we have this first equation and we have third equation. If you see in first equation and third equation, a plus b is common. So if I subtract 3 from 1, so 1 minus 3 will give me a plus b plus c is equal to minus 1. A plus b is equal to 1. So if I subtract them, so this will become minus. So this will go off, this will go off, this will be c is equal to minus 2. Okay, so I got the value of c. Now this c I can put in the equation 2, and also I can put say a in terms of b in equation 2, so that I get the value of b. Okay, so let me do that. So from 3 we have a is equal to 1 minus b. Why I'm doing 1 minus b and not 1 minus a is equal to b is because I'm trying to eliminate a and c so that I can get the value of b directly. Fine. So let me put this in equation 2. Putting a and c in equation 2, we get 4a, that is 1 minus b, plus 2b plus c, c is my minus 2, is equal to minus 8. Okay. So now from here I will have 4 minus 4b plus 2b. This 2 goes on the other side, it will become plus 2 and it will give me minus 6. So this 4 also I can take on the other side. So this gives us, this will be minus 2b is equal to minus 10, which implies b is equal to 5. So this is the value of b. Okay. So that's how we solve the equation. So because x is equal to 1 and x is equal to 2 were the solution of the equation, so they satisfy this particular equation. We got 3 equations and we solved for the value of b. Let's do one more question. There is some problem. So next question says, a polynomial in x of degree 3 vanishes when x is equal to 1 and x is equal to minus 2, and has the values 4 and 28 when x is equal to minus 1 and x is equal to 2 respectively. Then find the polynomial when x is equal to 0. Simple. So when he says the polynomial in degree x, a polynomial in x of degree 3, so that means I will have the polynomial of the form f of x is equal to say ax cube plus bx square plus cx plus d is equal to 0. So this is my polynomial equation. So he says that this particular equation vanishes when x is equal to 1 and x is equal to minus 2. So one way we can do is we can put the value of x as 1 and we can put the value of x as minus 2, and then we get two relations in a, b, c, d. And then we can put x is equal to minus 1 and equal to 4, and we can put x is equal to 2 and the value equal to 28, and then we get 4 equations and then 4 unknowns. Just like previous question, we can again solve a similar way. Otherwise, so that's one way of doing it. Otherwise, another way we can approach this question is, because we know that x is equal to 1 and x is equal to minus 2 are the roots of this particular equation. So this equation can be rewritten as, say, x minus 1 multiplied with x plus 2, and I don't know the third root because it's a cube, but because it's a, he has mentioned it has a degree 3, so I know that there has to be a root. Okay, so so that root, let me take it as mx plus n. So this is the factor which I'm taking, and this particular cubic polynomial I'm writing in this form. M and n are unknown to me, so then this, it becomes 0. Fine. So what I have done is I have basically written the cubic polynomial or the polynomial of degree 3 in this form, where x is equal to 1 and x is equal to minus 2 are the roots of this particular polynomial. So now what I need to find out is just m and n. So other two conditions what he has given is when x is equal to minus 1, f of minus 1 is equal to 4. So if I put x is equal to minus 1 over here, this will give me minus 1 minus 1 minus 1 plus 2 minus m plus n is equal to 4. Okay, so this is nothing but minus 2, this will be 1, minus m plus n is equal to 4. So if I just simplify it a little bit, Let me multiply with the minus sign. This will give me m minus n and 2 on the other side. So this will give me 2. So this is my first equation. Now the second equation is when I put x is equal to 2. So f of 2 is equal to 28 because f of minus 1 was 4 and f of 2 was 28. The values are given for those values, for those particular numbers. So if we put f is equal to 2 in this equation, we will have 2 minus 1, 2 plus 2, 2m plus n is equal to 28. So let me again write it 28. Okay. So this implies 2 minus 1 is 1 and this is 4. So if I take 4 on the other side, it will be 2m plus n is equal to 7. Fine. So this is the second relation which I have got. So let me just add 1 and 2 because here I have minus n and here I have plus n. So just simply add 1 plus 2 will give us 3m is equal to 9, which implies m is equal to 3. Okay, now put this m is equal to 3 in equation 1. We will get 3 minus n is equal to 2, which implies n is equal to 3 minus 2 is equal to 1. So I got m is equal to 3 and n is equal to 1. So basically my f of x is x minus 1 multiplied with x plus 2. mx plus n, m is 3. So 3x plus 1 is equal to 0. So this is my given polynomial. This is my polynomial which is needed. So now he's asking us find the value of polynomial when x is equal to 0. So let's simply put x is equal to 0. So this will be minus 1. This will be 2. This will be 1. So this is the value when x is equal to 0. So this is how simple concept here what we have used is because the polynomial vanishes at x is equal to 1 and x is equal to minus 2. That means they are the roots of that particular polynomial. So the polynomial can be written as this form. Okay, where x is equal to 1 and x is equal to minus 2 are the roots. So next we'll be discussing on geometrical meaning of roots. Roots are also sometimes called as zeros. Sometimes instead of using the terminology roots of an equation, we can also call them as zeros of an equation. So k is a zero of f of x. Then we have f of k is equal to 0. Okay, so when we say that k is a root or a zero of an equation, then it basically means that when we put k in that particular equation, then the value becomes 0. So what it basically means is, suppose I have an equation, say y is equal to x plus 3. No, okay, f of x is equal to y is equal to x plus 3. So what it means is this particular equation will become 0. X plus 3 is equal to 0. For what value of x? That is when x is equal to minus 3. I'm just taking the 3 on the other side. For x is equal to minus 3, this particular f of x, that is x plus 3 becomes 0. So that basically means f of minus 3 is equal to 0. So it means that x is equal to minus 3 is a root of the equation f of x is equal to x plus 3. Geometrically, if we want to understand it, it is nothing but if you draw the Cartesian plane. So this is my x-axis, this is my y-axis, this is 0 origin. So y is equal to x plus 3. So this will look like something like this. Anyway, the straight lines will discuss elaborately on how depending on the slope and depending on the y coordinate, how do we plot the graph of straight line. But basically, this is how y is equal to x plus 3 look like. So this graph y is equal to x plus 3 will cut the x-axis at minus 3 comma 0. So when I say x is equal to minus 3 is the root of this equation, that means this is the point where the graph cuts the x-axis. So whenever the graph cuts the x-axis, so that particular point where it cuts, that is called the root of the equation. So when we have a quadratic equation, say suppose let me take quadratic equation of x square minus x minus 2. I'm just taking some example. Say f of x is equal to x square minus x minus 2. So this is my quadratic equation. If I want to find out roots of this equation, that is basically I have to find out the points for which this value is equal to 0. So if I write in the factor form, this will be x square minus 2x plus x minus 2 is equal to 0, which is nothing but x minus 2, x plus 1 is equal to 0. That is x is equal to minus 1 comma 2. So my roots in that particular case is x is equal to minus 1 and x is equal to 2. So that basically means that this graph will cut the x-axis. In fact, if we plot it, say this will be my minus 1 and this is 1, this is 2. 1, 2, 0, minus 1. So the graph will cut the x-axis at minus 1 and 2. So it will come something like this. Go like this. So this is how the graph of x square minus x minus 2 look like. So root means basically the point where this graph cuts the x-axis in simple terms. Okay, so the next thing which we'll be discussing is key points for solving an equation. Okay, so the first thing which we have to take care while solving the equation is the domain of the equation. So the final solution, whatever we are getting after solving for x, it must satisfy the domain of the equation. So this is what we have to take care. So let's take a simple example. Suppose I need to solve x square minus 2x minus 3 by x plus 1. I'm just taking a simple example. So the general tendency of the students is, because this is on the denominator, so they just take it on the other side, cross multiply, and then they are left with x square minus 2x minus 3 is equal to 0. And if you factorize it, you will get x minus 3 multiplied with x plus 1 is equal to 0. So then we get x is equal to 3 and minus 1. But if you observe carefully, x is equal to minus 1 will not fit in this given equation, because when my x is equal to minus 1, the denominator becomes infinite, which is not allowed in maths. You cannot have some number k by 0. So this is a sin in mathematics. So this is not defined. So that's why x is equal to 3 is a solution of this, which perfectly satisfies. But x is equal to minus 1 is not a solution. So that's why in this case, our solution will be, solution is x is equal to 3. X is equal to -1, we don't consider because it doesn't satisfy the domain of this equation. What is the domain of this particular expression is? The domain is, this expression is satisfied for, I'm just talking about the expression, not the equation. This expression will exist for x belongs to R other than -1, except -1. This will exist for all R. But this particular equation will be satisfied when x is equal to 3. Because when x is equal to -1, this will go to infinity. So that's why we don't consider that. So this is one thing that we have to be very vigilant about, where my denominator is taking. Is there some value for which the denominator is becoming 0? So that cases we should always exclude from the solution. And another example, let me take. Suppose I have to solve, say, x cube minus 4x under root x square minus 1 is equal to 0. So if I need to solve this equation, you can simply write it as x multiplied with x square minus 4. This can be written as x plus 1, x minus 1 is equal to 0. So this x square minus 4 can be rewritten as x minus 2, x plus 2 under root x plus 1, x minus 1 is equal to 0. So what are the solutions for this? X is equal to 0, 2, minus 2, 1, minus 1. So this is the solution which we are getting. But here if you see, we know that if I have a function f of x which is under square root, so that means f of x should be greater than equal to 0, and square root of f of x also will be greater than equal to 0. Anyway, so in this particular question, we are concerned with this fact that whenever some function goes inside square root, that must be greater than equal to 0. So here also our domain will have x square minus 1 greater than equal to 0. So that means x minus 1 multiplied with x plus 1 should be greater than equal to 0. Now if we use the sign rule, we have this as origin, this as 1, this as minus 1. So here I'll have plus, here I'll have minus, here I'll have plus. Because the powers of x minus 1 is odd, so that's why the sign is changing. And x plus 1, the power is again odd, so that's why again the sign is changing at minus 1. So for values less than minus 1 and for greater than 1, this will be greater than equal to 0. So basically my x belongs to minus infinity to minus 1. This is closed here, open here, union 1 to infinity. Okay. But if you see, in this particular solution which we have got, 0 doesn't fall in this interval. 2 is okay, minus 2 is okay, 1 is okay, minus 1 is okay, because it's closed interval, so that's why we can include those values. But 0 doesn't fall. So that's why our solution set is minus 1, 1, 2, minus 2. This is our solution set. We will not take 0 in our solution, because when x becomes 0, this the expression which is inside the square root, that becomes less than 0, which is not allowed, because inside square root the expression always should be greater than equal to 0. Okay, so the next, so this was the first one, that is we have to be very much vigilant about the domain of the equation. So the first thing which we should take care is that the denominator should never become 0, and the second thing is whatever goes inside square root should be greater than equal to 0. Okay, so then let's talk about the second thing, that is extraneous roots. So sometimes what happens, like while we are solving the domain may expand and give some extraneous roots. If we take an example like x square is equal to x minus 2. So generally the tendency of the students while solving this expression is, okay, fine, I have a square root here. So to remove the square root, let me square on both sides. So this becomes x is equal to x minus 2 whole square. Okay, so then what they will do, x is equal to x square minus 4x plus 4, which will be x square. If I take this inside, 5x plus 4 is equal to 0. This will be x minus 4, x minus 1 is equal to 0. That is x is equal to 4 and x is equal to 1. But if you put the values back in the equation, when x is equal to 4, my LHS is square root of 4, which is equal to 4 minus 2. So this is 2 is equal to 4 minus 2, 2. So this is perfectly satisfying. When x is equal to 1, I have LHS as under root 1, and this is 1 minus 2, which is minus 1, and this is 1. So which is, right? 1 is not equal to minus 1. So this extra root I have got because I have squared the equation. So whenever we are squaring the equation, there is always possibility of getting an extra root. So that's why it's always advisable that you put back the values in the original equation and see whether it satisfies or not. If it is not satisfied, then you drop the particular solution and then just go ahead with the solution which satisfies. That is x is equal to 4 in this case. Okay. So that's how we have to take it. Now, why x is equal to why x is equal to 1 is not satisfying here in this equation is again very simple. Because as I mentioned, anything which goes inside square root has to be greater than equal to 0. So when I have under root of f of x, that means my f of x should be greater than equal to 0, and square root of f of x also should be greater than equal to 0. So in this case, if I have under root of x, so this basically means my x should be greater than equal to 0. That means my domain of x is x belongs to 0 close to infinity. But here, along with that, I should also consider that under root of f of x is also greater than equal to 0. That means x minus 2 is also greater than equal to 0. That means x is greater than equal to 2. So basically, if I take intersection of these two, I will get x belongs to 2 to infinity. It is closed and it is open. So my actual domain is that x is belonging to 2 to infinity. But here I have got x is equal to 1, which doesn't come in this domain, which is before 2. So that's why I am neglecting x is equal to 1 and I am taking only x is equal to 2. Fine. So whenever we are squaring, the domain expands and gives us an extra root. Now the next thing is third one, loss of root. So sometimes what happens when we are performing some operation, there could be cancellation of a root. So suppose if I have a expression like this, x multiplied with x minus 2 is equal to x minus 2. So generally what some students do is, okay, here I have x minus 2, here I have x minus 2. So let's cancel both of them. So let's see what happens if we cancel. So if we cancel it, we are getting just x is equal to 1 as the root. But if we don't cancel it, ideally how we are supposed to solve it is, we multiply this, we don't cancel, because whenever you cancel, you lose a root. So we should not cancel it. And in fact, we should multiply x with this term, and then this will be equal to x minus 2. Bring all the terms on one side, which will give us x minus 3x, x square minus 3x plus 2 is equal to 0. If you write in the factors form, this will be x minus 2, x minus 1 is equal to 0. So that basically means x is equal to 2 and 1 and 2, anything you can write. So here I am getting two roots. But here, because I cancelled it, I'm getting only one root. So we should always be careful that we don't cancel off the roots. Otherwise, we lose the roots. So it's all, okay, let's recap. There are three different points we should take care while solving the equation. One is the domain. In case of domain, we should make sure that again, two things in this. One is that denominator should never be equal to 0, so that we should make sure. And whatever square root terms are there, inside square root, we should always have terms greater than equal, or the expression greater than equal to 0. So sometimes when we are squaring the equation, then we may get some extra roots. So to avoid that, we should always put back the values and see whether the roots which we have got, they are actually satisfying the equation or not. And then sometimes there could be common roots on both sides of equal to. We should not just directly or blindly cancel them. In fact, we should take all the terms on one side and only then solve it. Okay. So next, we'll be seeing equations reducible to quadratic. So sometimes it may happen that some questions are given in such a way that externally it may not directly appear a quadratic equation, or it may appear quadratic, but it may not be directly possible to solve in a quadratic form. So in such cases, we have to substitute some particular part of the expression as some variable and then go ahead solving. I think with this example, things will get more clear. Suppose I have, say, solve under root of 5x square minus 6x plus 8 minus 5x square minus 6x minus 7 is equal to 1. Suppose this is my equation which I'm supposed to solve it. So externally, I may feel that no, where I should I square on both sides, or because how do I proceed? Of course, one way is that you take this term on the other side and then you square and then you do. That's one way of doing it. Another way is to simplify the whole thing. We can take some part of the expression. Say I'm taking 5x square minus 6x, because I'm seeing 5x square minus 6x is here also, and this particular expression also. So if I put that as another variable y, so then my problem becomes little simple. So this becomes under root of y plus x minus under root of y minus 7 is equal to 1. Now it looks quite simple than this. So now let me take this term on the other side and square on both sides. So this will be y plus 8 is equal to 1 plus under root y minus 7 whole square. Again, because I'm squaring on both sides, I should be cautious with the extra root which I'll be getting. Okay, so that I should make note of it in the end. So this will be 1 plus y minus 7 plus 2 under root y minus 7. So if I take all y's on one side, in fact, I can cancel out this y with this. So I will get ultimately 8. This will be minus 6. So this will come on here. Okay, let me write it. Plus 6 is equal to 2 under root y minus 7. So this is 14, and 2 if I take, this will give me 7 is equal to y minus 7. Again, let me square on both sides, because now there won't be any extra root because both are positive terms. So this will be 49 is equal to y minus 7, which is y is equal to 49 plus 7, 56. Okay. So y is equal to 56 is my solution for this equation. This is not my final solution. This is solution for this equation. Now I have to put this value for y and then find out what will be the values of x. Okay. So 5x square minus 6x is equal to 56. If I take this on the other side, this will give me 5x square minus 6x minus 56 is equal to 0. Okay. So now I need to factorize it. So I need two terms such that the product of the terms is 56 into 5, that is 30, 3, 25, 28. The product is 280 and the sum or difference is minus 6. So 280 can be also written as 28 into 10. So this has the product as this, but sum is not this. Otherwise, we can write it as, say, 14 multiplied with 20. Yeah, so this will give me difference as minus 6 and product as 280. So I can rewrite this as 5x square minus 20x plus 14x minus 56 is equal to 0. So I proceed solving it. It will be, let me take x common. Sorry. Yeah. So this will be x 5x minus 20 plus, okay, in fact, I could have taken 5x common. So this will be x minus 4 is equal to 0. Let me take 5 also common. So it will be 5x plus 14 multiplied with x minus 4 is equal to 0. X is equal to minus 14 by 5 or 4. So now let's put back the values and see. In fact, I don't think so we'll get any extra value here because the squaring which we had done, that was done in case of y, not in case of x. So x we have directly put as y. This particular expression in x we have directly put as y, and then we have got this. So no squaring, nothing we have done. So I don't think so it will not satisfy. But anyway, you can check and then see whether both the values satisfy or not. Okay. So this will be my solution. So the expression may not be, in this case, it is quadratic inside square root, but here we are taking a part of the quadratic as another variable y and then reducing it into simple quadratic equation. Fine. So let's do another question. So I have 4 power x minus 5 multiplied with 2 power x plus 4 is equal to 0. So now if you see externally, this equation doesn't look like a quadratic. Now we have 4 power x, 2 power x. But this can be reduced to a quadratic equation when we take 2 power x is equal to y. So what happens when we take 2 power x is equal to y? My 4 power x will be equal to y square. Yes, because 4 is equal to 2 square. So this will be equal to y square. So this equation gets reduced to y square minus 5y plus 4 is equal to 0, which is nothing but y minus 4, y minus 1 is equal to 0. That is y is equal to 4 and 1. Now when y is equal to 4, what is my x? 2 power x is equal to 4, which implies x is equal to 2. So this is one solution. Now when my y is equal to 1, that means 2 power x is equal to 1, which is possible when x is equal to 0, because we know 2 power 0 is 1. Anything to the power of 0 is 1. So in this case, when x is 0, then it becomes 1. So my x is equal to 0 and 2. This is my solution of this equation. So externally, sometimes the equation may not look like a quadratic, but when you substitute a part of expression as some variable, then we can reduce it into quadratic form. Let's do another example based on this. Solve 3x square minus x plus 4 power x square minus x is equal to 25. Okay. So here we have 3 power x square minus x and 4 power x square minus x. So on the other side we have 25, right? One thing we can do here is this 25 can be written as 9 plus 16, which is nothing but 3 square plus 4 square. So when we have 3 power something plus 4 power the same thing is equal to here some terms, then we can directly equate them. So then I can write x square minus x is equal to 2, because here also if x square minus x is 2, it will satisfy, and x square minus x is equal to 2, it will satisfy. So basically I have the equation as x square minus x minus 2 is equal to 0, which is x square minus 2x plus x minus 2 is equal to 0, which is x minus 2, x plus 1 is equal to 0. That is x is equal to 2 and minus 1. So this is my solution for this particular equation. Fine. So that's how we have to solve the equation. So if sometimes they may look like quadratic, we directly solve it. If they don't, then we have to use some specific substitution and then accordingly solve them. So the next thing which we'll be discussing is remainder and factor theorem. Okay. So let's first discuss about remainder theorem. We'll discuss them one by one. In fact, both of them are connected, but still. So let's first understand what is remainder theorem. So what remainder theorem says is, if I have a polynomial, say f of x, and if it is divided, if f of x is divided by a linear function x minus k, then the remainder is f of k. So what is happening here is, suppose I have a polynomial which is f of x. When it is divided by some function x minus k, then the remainder which I'll be getting will be f of k. So we have, whenever the one which gets divided is called dividend. So when we divide it with a divisor, we get something called quotient. This is quotient. The quotient, when it is multiplied with divisor and added with remainder, will give us the dividend. So dividend is equal to quotient multiplied with divisor plus remainder. Okay, so let me write in a simple way, because here f of x is being divided. So f of x is my dividend and divisor is x minus k. So the coefficient which I'll get will be, say, f of q of x multiplied with x minus k, and my remainder is, say, r. Fine. So now if I take f of k, if instead of x, if I put f of k, this will give me q of k multiplied with k minus k plus r. K minus k is nothing but 0. So my f of k will be equal to r. So when I'm dividing a function f of x with a linear function x minus k, then the remainder will be f of k. That is my remainder. Okay. So if the degree of the polynomial which I'm with which I'm dividing, say, if n degree polynomial is divided by m degree polynomial, maximum degree of the remainder polynomial is m minus 1. So if n degree polynomial is divided with a m degree polynomial, in the previous case, our dividend was a linear, so m degree, in that case it was 1. The degree 1 polynomial was dividing the nth degree polynomial. Then the maximum degree of remainder will be m minus 1. Suppose I have say any function f of x, and it is getting divided by a quadratic, say ax square plus bx plus c. So after completing the whole division process, ultimately the remainder which I'll be getting will be a linear px plus q form, right? So it will be always be 1 degree less than the dividend. Okay. So let's do a simple example. Okay, let's expand it. So the question says if the expression, so here's a given expression, has remainder 4x plus 3 when divided by x square plus x minus 2. Find the values of a and b. Basically, he has told that we have f of x is equal to ax power 4 plus bx cube minus x square plus 2x plus 3. Okay, so this is my expression, and it is getting divided. That is my dividend, and that is my divisor is x square plus x minus 2. So this x square plus x minus 2 can also be written as x square plus 2x minus x minus 2, which is x plus 2 multiplied with x minus 1. Okay, so basically this particular expression is getting divided by this expression. So we know that if an expression is divided by a linear expression, that is x plus k, x minus k, if x minus k divides this particular equation, then my remainder is f of k. So now if I, instead of dividing with both of them, let me divide with one by one. So if I divide with only x plus 2, then my remainder will be, say, when I take x plus 2, my k in this case is minus 2. So that means my remainder will be f of k, that is f of minus 2, which is 4 multiplied with minus 2 plus 3. So this will give me minus 8 plus 3, which is minus 5. Okay. And this is f of minus 2. So instead of this x in this particular expression, we put minus 2. So this will be a minus 2 to the power of 4 plus b minus 2 to the power of 3 minus of minus 2 square plus 2 minus 2 plus 3 is equal to minus 5. So this is what is the relation I have got. Okay, so let me simplify it a bit. 2 power 4 is 16. So this is 16a plus, okay, this will be minus 8b. This will be 4. So minus 4. This will be minus 2, minus 4 again, plus 3 is equal to minus 5. So this will give me 16a minus 8b. Let me take all the terms on the other side. So this will become minus 8 and this will become plus 8. So this will be equal to 0. So that is basically 2a is equal to b. This is a simple relation which I have got. This is my first equation, a and b. Okay. Now let me consider, this is the relation which I have got when I considered x plus 2. Now let me take x minus 1. So when I take x minus 1, in that case, my k is equal to 1. Fine. So let me write what is my remainder. So if k is equal to 1, my remainder is equal to f of k, which will be equal to, now put x is equal to 1 in this remainder which is given. So this will be 4 multiplied with 1 plus 3, that is 7. And what is f of 1? That is f of 1 is equal to 7 is equal to, so in this particular expression we put x is equal to 1. So this will give us a multiplied with 1 power 4 plus b 1 power 3 minus 1 square plus 2 1 plus 3 is equal to 7. So this is a plus b minus 1 plus 5, 2 plus 3, I am writing 5, is equal to 7. Okay, so this will be a plus b is equal to, let me take all the terms on the other side, this will be 8 minus 5 is 3. So a plus b is equal to 3 and 2a is equal to b. So there, if you solve this equation 1 and 2, you just, in fact, you can directly tell because b is twice of a. So we will get a is equal to 1 and b is equal to 2 because the sum is 3 and here a is twice of a is b. So this will be the value of a and b. Okay. So this is how we have to use the remainder theorem and then solve. So the next thing we have is factor theorem. So what factor theorem exactly is? It's just a special case of a remainder theorem. Now suppose if I have expression f of x is equal to, it is divided by k, then I get a coefficient and I get a remainder. So previously we had seen that this remainder will be nothing but x minus k. I get a coefficient plus f of k because f of k is my remainder as per remainder theorem. Now if what factor theorem says, if f of k is equal to 0, then f of x is equal to x minus k multiplied with fq of x. So it basically says when the f of k is equal to 0, then x minus k perfectly divides the dividend. It will not have any remainder. So it's just nothing but extension of remainder theorem. So basically when the remainder vanishes, that means the factor perfectly divides that particular dividend. Okay. So let's solve a simple question to make our understanding more better. Fine. So now the question says, use the factor theorem to find the value of k for which x a plus 2b, where a and b are not 0, is a factor of this particular expression. So he has given an expression a power 4 plus 32b power 4 plus a cube multiplied with k plus 3. So this is the given expression. He is telling that find the value of k. This k we have to find out, for which a plus 2b is a factor of this particular expression. So if instead of a, if I just replace a with x, because when I say a, generally our mind assumes it's a constant. But if you see this particular expression is nothing but f of a. Basically, of course, it has some b's also, but this is nothing but an expression where we have a's, right? So instead of a, if I write it as f of x, so this will give me x power 4 plus 32b power 4, as it is I'm writing x cube b k plus 3. Okay. So this I have basically written the same expression in terms of x. Instead of a, I'm writing x. So this equation, this expression has x plus 2b. So as soon as I write x plus 2b, now it becomes easy for us to understand. Yes. So x plus 2b is a factor of this equation, this expression. So that basically means f of minus 2b is equal to 0. So that is minus 2b whole 4 plus 32b power 4 plus minus 2b whole cube b k plus 3. This will be equal to, this will be my 16b power 4 plus 32b power 4. This is minus 2 to the power of 3. So this will be minus 8 b cube and b. So this will be b power 4 k plus 3 is equal to 0. Okay, so the 0 I'm writing on the other side. So this implies b power 4, and b power 4 is common from each term. So I can take it outside, and because here I have 0, so that gets absorbed by 0. So this will be 16 plus 32 minus 8 k plus 3 is equal to 0. So this will be 48 minus 8 plus 3 is equal to 0, which implies, let me take this term on the other side. This will be 48 by 8 is equal to k plus 3. And 48 by 8 is 6 is equal to k plus 3, which implies k is equal to 3. So this is my value of k, which I have got. Okay, so it's not that always the equation will be in terms of x. Sometimes the expression could be also in terms of a's or b's, like that. But we have to understand properly where exactly we should apply this factor theory. Okay. So now let's go to the next topic, that is quadratic equations. So any equation of the form ax square plus bx plus c is equal to 0 is a quadratic equation. And of course, provided a is not equal to 0, because if a becomes 0, then it becomes a linear equation. And here we consider a, b, c belongs to real number. So they are real numbers. So in this case, we have two cases. There is something called d, which is called discriminant, which is my b square minus 4ac. So if this discriminant, that is d, is equal to 0, then we say the quadratic equation has equal roots. Okay, so when the discriminant becomes equal to 0, then it has equal roots. When discriminant is not equal to 0, again we have two cases. In one case, discriminant is greater than 0. Other case, discriminant is less than 0. So when discriminant is greater than 0, so here we will have real and distinct roots. And when discriminant is less than 0, then we will be having imaginary roots. So when I say imaginary roots, it will be of the form p plus I cube and p minus I cube. Okay. So now again, when the roots are real, depending on whether my D is perfect square or D is not, let me write it like this, is not a perfect square. Depending on whether the discriminant is a perfect square or not, again I will have, if it is perfect square, then I will have rational roots. If it is not a perfect square, then I'll have irrational roots. So irrational roots will be of the form, say a plus, okay, already we have taken a, so let's take m plus under root n and m minus under root n. So whenever we have complex roots or whenever we have irrational roots, they always occur in pair. If m plus under root n is a root, then m minus under root n has to be a root. Similarly, for the case of complex numbers, yes, so they always occur in pair. So depending on what is the value of d or the discriminant we get, that is d square minus 4ac, we have different cases for this quadratic equation. Okay. So let's do this simple question. If the roots of this equation, the given equation is a b minus c x square plus b c minus a x plus c a minus b is equal to 0. If the roots of the equation are equal, so that means it has equal roots. Show that 2 by b is equal to 1 by a plus 1 by c. So 2 by b is equal to 1 by a plus 1 by c. This is what we have to prove. So it basically means that my a, b, c are in HP. Anyway, when we'll discuss series and progressions chapter, so there we'll discuss in detail about the harmonic progression. So this particular equation has equal roots. So what is the condition for equal roots? My discriminant has to be 0. What is my discriminant? Okay, here A, B, C are already used. So in case if I have a quadratic equation like this, ax square plus bx plus c is equal to 0, then my discriminant is b square minus 4a multiplied with c. So this will be, in this case, this is my a, okay, this is my a, this is my b, and this is my c. So my b square will be b c minus a square minus 4 AC, A multiplied with C. So this will be AC, B minus C, A minus B is equal to 0. Okay. So this will give me B square. So let me expand it. So this will be B square C square minus plus A square minus 2AC minus 4AC. If I multiply them, I'll get AB minus B square minus AC plus BC is equal to 0. So let's go ahead simplifying. B square C square plus A square B square minus 2ac b square minus 4a square bc minus 4ac. Okay, this will be minus minus plus square plus 4a square c square minus 4ab c square is equal to 0. So this is the expression which we have got. Okay, so now let's see if we can cancel or simplify some terms. So we have, let's write b square c square plus a square b square. So here also I have a square c square. So let me bring this term here, 4a square c square, and then okay, this is 2acb square, this is 4acb square. So I will get plus 2ac b square minus 4a square bc minus 4ab c square is equal to 0. So if you observe carefully, if instead of this 4a square c square, if I write it in this way, b square c square plus a square b square plus 2ac whole square plus 2 multiplied with ab bc minus 2 multiplied with 2ac ab minus 2 multiplied with 2ac equal to 0. So this is of the form say I have PQR. So this is of the form P square plus Q square plus R square plus 2PQ minus 2PR minus 2QR is equal to 0. So this would give me nothing but P plus Q minus R whole square is equal to 0. So using this property in this particular equation, I will get B square. Let me remove the squares. So I will get BC plus AB minus 2AC whole square is equal to 0. So when the whole square is equal to 0, that means BC plus AB minus 2AC is equal to 0. So if I take this 2AC on the other side, I will get BC plus AB is equal to 2AC. Now, because my A, B, C are not equal to 0, I can divide both my RHS and LHS with A, B, C. So this will give me BC by ABC plus AB by ABC is equal to 2AC by ABC. So this BC will go with this AB will go with this AC will go with this. So I'll be left with 1 by A by 1 by C is equal to 2 by B. So this is what we had to prove. Okay, so simple. We have just taken the condition that for equal roots, we have to take the discriminant as equal to 0. So that's the simple funda which we have used in this particular problem. Okay, so let's take another simple question. Find the quadratic equation with rational coefficients whose one root is 1 by 2 plus root 5. So he has given that one of the roots of a quadratic equation is 1 by 2 plus root 5. So this 1 I rationalize it, because in the denominator we don't want irrational terms, so let's rationalize it. We can do that by multiplying the numerator and denominator with 2 minus root 5 and 2 minus root 5 here. So this will be 2 minus root 5 by 4 minus 5. This is 2, 4 I have got, because it is 2 square minus under root 5 square. So this will be minus 1. So minus goes up. This will be under root 5 minus 2. So we have seen that if my one of the roots is under root 5 minus 2, then other root will be the corresponding conjugate, in the sense the corresponding with the negative sign. Just like we had, if p plus root q is a root, then p minus root q has to be the second root. So in this case, if I rearrange and write it in a little proper way, this will be minus 2 plus root 5. So minus 2 plus root 5 is a root, so which implies the roots of quadratic equation are minus 2 plus root 5 and minus 2 minus root 5. So these two will be the roots, because if this is the root, then this has to be the root. That's how they occur in pairs. Okay, so then we have sum of roots is equal to minus 2 plus root 5 minus 2 minus root 5. So these root terms will go away. I will be getting minus 4. And we have product of roots minus 2 plus root 5 multiplied with minus 2 minus root 5. So this is, if I take, okay, let me write it in this way, minus 2 square minus root 5 square. So this will be 4 minus 5, which is minus 1. So we know that if I have the sum of the roots as s and product of the roots as p, so this is s and this is p, then the quadratic equation is x square plus s x plus p is equal to 0. Okay, this is minus sx plus p is equal to 0. Because the sum of the roots is minus b by a, so the quadratic equation will be s square minus s plus p is equal to 0. In this case, if you take the sum of the roots, this will be alpha plus beta if they are the roots. So this will be minus of minus s, which is s, that is my sum of the roots. And product of the roots will be p by 1, that is 1 is here, the a, which is p. So that's how I'm getting the sum of the roots and product of the roots. So if s is the sum of the roots and p is the product of the roots, then the quadratic equation will be x square minus sx plus p is equal to 0. So if I put the values of s and p, I will get x square minus of minus 4x plus of minus 1 is equal to 0, which implies x square plus 4x minus 1 equal to 0. So this is my required quadratic equation, which has one of the roots as 1 by 2 plus under root 5. So with this note, let's write down this also. For quadratic equation ax square plus bx plus c is equal to 0. Sum of roots is equal to s is equal to minus b by a, and product of roots, which is p, is c by a. So when I have a sum of the roots, which is alpha plus beta, where alpha and beta are the roots of this equation, then it is given by minus of b by a, and similarly product of the roots is given by c by a. Okay, go ahead doing one simple question. Form a quadratic equation with real coefficients whose one root is 3 minus 2y. So he's asking us to find the quadratic equation which has real coefficients whose one root is 3 minus 2y. Again, as we have discussed, that complex roots also occur in pairs. So the roots of equation will be 3 minus 2y and 3 plus 2y. Because if 3 minus 2y is a root, then 3 plus 2y must be a root of it. So then we have sum of the roots as 3 minus 2y plus 3 plus 2y. So this imaginary part will go away. I'll be left out with 6. Product of the roots will be 3 minus 2y multiplied with 3 plus 2y. So this will give me 3 square minus 2i whole square. So this will be 9 minus I square is minus 1. So this will be minus of 4. So this will be 13. Okay. So again, as we know, if S and P are the sum and products respectively of a quadratic equation, then the quadratic equation is x square minus sx plus p is equal to 0. So if I put the corresponding values, so I will get x square minus 6x plus 13 is equal to 0. So this is my quadratic equation whose one root is 3 minus 2y. Okay, so this is how we solve when we have a quadratic equation with imaginary roots or irrational roots. So let's do another question, another type of question. So the roots of the equation ax square plus bx plus c is equal to 0 are alpha beta. Find the equation whose roots are 1 by alpha and 1 by beta. Of course, there are 3 different bits which he is asking us to find. So basically, there is a given equation, that is ax square plus bx plus c is equal to 0. This has the roots alpha comma beta. Now he's asking us to find the equation whose roots are, the first one is 1 by alpha and 1 by beta. Okay. So whenever such question is given, one thing you will always observe is that whenever they are changing the roots, they are giving the new roots will change symmetrically. If alpha is changed to 1 by alpha, then beta will also be changed to 1 by beta. That's how they will frame the question. They will not say that oh, is changing in one way and beta is changing in another. That won't generally be asked. So here you see, alpha is becoming minus alpha, beta is becoming minus beta, and here also it's symmetrical. So alpha and beta will be changing in a symmetrical way. Generally, that's how they frame the questions. So in this case, if you see, alpha and beta satisfy this particular equation. So if I take, say, 1 by alpha is equal to y, which will give me, I'm taking some variable y, which is 1 by alpha, which will give me 1 by y is equal to alpha. But I know that alpha satisfies this equation. So that means A alpha square plus B alpha plus C is equal to 0. Now instead of alpha, if I put 1 by y, I will get 1 by y is a variable which is equal to alpha. So this will be B by y plus C is equal to 0. If I simplify this, this will be A plus by plus cy square. The highest order term first, then I'll get cy square plus by plus a is equal to 0. So this is the equation. Now you can replace from this equation y with x. So cx square plus bx plus a is equal to 0. So this is the equation which will have the roots 1 by alpha and 1 by beta. So what we did is we took 1 by alpha. Of course, because we are taking 1 by alpha, 1 by beta is also assumed to be changing accordingly because both of them are symmetrical. So 1 by alpha is equal to some variable, and then that variable we are putting in the given equation instead of alpha, and then we are getting an equation. And we had taken any variable, so that variable we can replace with x or y or anything we can take. So this is the quadratic equation in y, and this is the quadratic equation in x. So the roots of this equation will be 1 by alpha, 1 by beta. Why? Because my y I have taken as 1 by alpha. Now, if we take the second bit, that is, I need the equation whose roots are minus alpha and minus beta. So in this case, now we do the same thing, but this way. We take minus alpha is equal to y, which implies alpha is equal to minus y. So now a alpha square plus b alpha plus c is equal to 0. This equation is satisfied with alpha, so that's why we get over here. So instead of alpha, we can put minus y. So this will be a y square minus by plus c is equal to 0. Now this y can be replaced with x or any other variable. So this will be ax square minus bx plus c is equal to 0. This is the given, this is the required equation whose roots will be minus alpha and minus beta. Now let's take the third bit. Similarly, same way we'll have to do it. This is 1 minus alpha and 1 plus alpha. 1 plus alpha. Here we have 1 plus beta by 1 minus beta by 1 plus beta. Yes. So in this case, again, we take 1 minus alpha by 1 plus alpha is equal to y. So now we have to express alpha in terms of y. So this will be, you can use component or dividendo. So this will be 1 minus alpha plus 1 minus 1 plus alpha by 1 minus alpha minus 1 minus alpha is equal to y plus 1 y minus 1. So this is alpha goes off, 1 minus 1 goes off. So 2 by minus 2 alpha is equal to y plus 1 y minus 1. So this 2 and 2 I can cancel. If I take minus 1 on the other side, I will get 1 by alpha is equal to y plus 1 1 minus y. If I take the reciprocal, alpha is equal to 1 minus y by 1 plus y. So this is how I will get my alpha. Now again put back my alpha in the equation because it is the root of that equation. Now instead of alpha, I can substitute this. I will get a multiplied with 1 minus y plus y whole square plus b multiplied with 1 minus y 1 plus y plus c is equal to 0. So now we'll get a quadratic equation which will be our required quadratic. So let's simplify it. Let's multiply 1 plus y square throughout. So I will get 1 plus y square minus 2y plus here it will be b 1 minus y square plus c 1 plus y square minus 2y is equal to 0. Okay, so I had taken LCM and then done the simplification. So this will imply, let me take all y square terms at one place, a minus b plus c y square plus, if we take y terms on one side, this will be minus 2a. Okay, here we don't have any y term, this will be minus 2c. And then all constant terms will be a plus b plus c is equal to 0. So the required equation is a minus b plus c y square minus 2a plus c y plus a plus b plus c is equal to 0. So this is my required equation, which will have the roots as 1 minus alpha by 1 plus alpha, 1 minus beta by 1 plus beta. Okay, so this is how we approach the problem. So next, let's discuss about common roots. So suppose I have a1x square plus b1x plus c1 is equal to 0 is one quadratic equation, and a2x square plus b2x plus c2 is equal to 0. So I have these two quadratic equation, and my condition is that one root is common. So this is the first condition I'm taking, that one root is common in these two equations. So I consider let the common root be alpha. So these two equations, the common root which is considered as alpha. So because alpha is a common root in equation 1 and 2, alpha will satisfy both of these equations. So let's put alpha in this. So alpha will satisfy both these equations. So now using this condition, these two equations, I can solve for alpha square and alpha. Just like we have linear equations in two variables, say a1x plus b1y plus c1 is equal to 0, and a2x plus b2y plus c2 is equal to 0. So there are two equations in two variables. Similarly here, one variable I'm taking as alpha square and another variable I'm taking as alpha. So this will be b1, b2, c1, c2, a1, a2, again b1 and b2. So this will be alpha square by b1 c2 minus b2 c1 is equal to alpha by c1 a2 minus a1 c2 is equal to 1 by a1 b2 minus a2 b1. So my alpha square will be b1 c2 minus b2 c1. So basically this is how we are doing. First b1 c2 minus b2 c1, and then here c1 a2 minus a2 c1, then a1 b2 minus a2 b1. Okay, so this will be b1 c2 minus b2 a2 minus a2 b1, and alpha is equal to c1 a2 minus a1 c2 by a1 b2 minus a2 b1. So we know that alpha square is square of this alpha. So that's how we can say that this term is also square of this term. So if I square this, basically, C1 A2 minus A1 C2 by A1 B2 minus A2 B1. So if I square this guy, this expression, I will be getting B1 C2 minus B2 C1 by A1 B2 minus A2 B1. And here, if you see the denominator, one factor is common. So I'll get C1 A2 minus A1 C2 whole square is equal to B1 C2 minus B2 C1 multiplied with A1 B2 minus A2 B1. So this is the relation which we'll be getting when we have one root common between these two equations. Yes, of course, we need not remember or mug up this thing. The easy way to remember this is, suppose I have A1 x square plus B1 x plus C1 is equal to 0. A2 x square plus B2 x plus C2 is equal to 0. So then you have to remember like this. So first B1 C2 minus B2 C1. This is the term. A1 B2 minus A2 B1. This is the term. And for this, it will go from here to big cross. From A1 C2 minus A2 C1 square. Okay. So first here, then here, and the final one here. So that's how we can remember this particular relation. So this is the condition when we have one root as common in these two given equations. So the next one is when both roots are common. So the quadratic equation C1x square plus B1x plus C1 is equal to 0 and A2x square plus B2x plus C2 is equal to 0. If they have both roots common, then the condition is A1 by A2 is equal to B1 by B2 is equal to C1 by C2. Because when we say that both roots are common, that means both quadratic equations are in fact identical. So that's how A1 by A2 is equal to B1 by B2 is equal to C1 by C2. Okay, so let's do a simple question. And here again we have to remember, we have discussed that if we have roots as irrational, if one of the roots is of the form p plus under root q, then other root will surely be p minus under root q. So if in questions, if sometimes he says that the two equations have a common root, that is p plus under root q form, then we have to understand that surely the other root also will be common. Okay. And the same thing applies when the roots are complex. If he says that p plus iq is a common root of two equations, then that means p minus iq is also common root. That means instead of considering the condition that only one root is common, we have to consider that both the roots are common for that particular equations. Okay, because again, this irrational roots and complex roots always occur in pair. So if one root is common, that means other root also must be common for both of them. Okay, so the question says if ax square plus bx plus c is equal to 0 and this particular equation have a common root and a, b, c are non-zero real numbers, then find the value of this expression. Okay, so let's write down the equations first. ax square plus bx plus c is equal to 0. bx square plus cx plus a is equal to 0. So how do we remember? We just have to cross and then a big cross here. So first write down the terms of the small cross. So it will be ac minus b square multiplied with ab minus c square is equal to the bigger cross a square minus bc whole square. Okay, so if we expand it, we'll get a square bc minus ac cube minus ab cube plus b square c square is equal to a power 4 plus b square c square minus 2a square bc. So this b square c square will go with this, and here I have a square b, here I also have a square b. So let me bring this here, and remaining terms I can take on the other side. I'll be left with 3a square bc is equal to a power 4 plus ac cube plus ab cube. So a is common on both sides, so I'll end up with 3abc is equal to a cube plus b cube plus c cube. What we need is a cube plus b cube plus c cube by abc. So let me take this abc over there. I'll get 3 is equal to a cube plus b cube plus c cube by abc. So this is the value which I'll be getting for this given expression. Relation between coefficients and the roots of n degree equations. So the relation between the coefficients of the equation and the roots of the equation. So when I have a quadratic equation, say ax square plus bx plus c is equal to 0, say alpha and beta are the roots of this equation. So the sum of the roots, alpha plus beta, we have seen, is given by minus b by a, and product of the roots is given by c by a. So this is for quadratic equations. Now suppose if I have a cubic equation means we have the maximum degree as 3. So say it is of the form ax cube plus bx square plus cx plus d is equal to 0. Then alpha, beta and gamma be the roots. Then sum of the roots, that is alpha plus beta plus gamma, is given as minus b by a. The sum of the roots taken 2 at a time, alpha beta plus beta gamma plus gamma alpha, is given by c by a, and product of the roots is given by minus d by a. Now similarly, if I have a biquadratic equation means the maximum degree I have is of 4. So this is ax power 4 bx cube plus cx square plus dx plus e is equal to 0. So in this case, again, the sum of the roots, say alpha, beta, gamma, and delta are the roots. So alpha plus beta plus gamma plus delta is equal to minus b by a. And if we take 2 times the roots and then take sum, so I'm writing it as sigma alpha beta. Okay, so sum of the roots taken 2 at a time. So this will be c by a. Now if I take sum of the roots taken 3 at a time, then this will be minus d by e. So taken 3 at a time basically means alpha beta gamma plus beta gamma delta plus gamma delta alpha plus delta alpha beta. Okay, so yeah, so that's how we'll be getting sum of the roots taken 3 at a time. Now if we take the product of the roots here, it will be e by a. Simple. So one thing we can always observe is whether we have quadratic or cubic or biquadratic, the sum of the roots is always minus b by a. And after that, when we take this product of the root, the sum of the roots taken 2 at a time, then it becomes c by a. Here, because taken 2 at a time, or the total product is the same. So that's why we are getting alpha beta is equal to c by a. And if you see, there is alternate plus minus sign, minus b by a, then c by a, in all the cases c by a, and then minus d by a, and then plus e by a. So minus, plus, minus, plus. So likewise, if we have nth degree equation, where an x power n plus an minus 1 x n minus 1 plus an minus 2 x n minus 2, so on, a0 is equal to 0. Suppose this is my this is my n degree equation. Then sum of the roots is, say, alpha, beta, gamma, delta, and so on are the roots of the equation. Then the sum of the roots, that is sigma alpha, I'm writing, will be always minus an minus 1 by an. This coefficient, the second coefficient by the first coefficient with a negative sign. And then the sum of the roots taken 2 at a time will be an by an minus 2 by an, and taken 3 at a time will be an minus 3 by an. Likewise, it will go. This will be with minus sign. So minus, plus, like that will keep on having the relation. Okay. So that's how we'll have the relation between the coefficients of the equation and the roots of the nth degree equation. Okay. So let's do a simple question before we proceed. There is some problem. Yes. So let's expand. If alpha, beta, gamma are the roots of the equation, so he has given a cubic equation. This is x power 3. Then find the value of 1 by alpha plus beta plus 1 by beta plus gamma plus 1 by gamma plus alpha. So this is what he wants us to find, given alpha, beta, gamma are roots of this equation. So when we have this equation, we can clearly say alpha, beta, gamma, the sum is how much? This will be 0 because this equation can be rewritten as x cube plus 0 multiplied with x square plus 4x plus 1 is equal to 0. Okay, so the second coefficient by the first coefficient, so this will be my sum of the roots, that is 0. Fine. So then alpha, beta, sigma will be equal to 4 by 1. So this will be 4. And alpha, beta, gamma, the product of the roots will be equal to minus 1 by 1. So this is minus 1. So we use these relations in solving this. So one way of doing it is blindly we take the LCM and then get the numerators and then simplify using this relation. Otherwise, if we use a little common sense, we'll understand that alpha plus beta is given and we have alpha plus beta plus gamma. So can I replace alpha plus beta with minus gamma using this relation? Because I know alpha plus beta plus gamma is equal to 0. So my alpha plus beta will be equal to minus gamma. So basically what I am writing is alpha plus beta is minus gamma. Similarly, alpha plus gamma is my beta plus gamma is minus alpha plus gamma plus alpha is minus beta. Okay. So now it's better to take LCM because now it's a simplified one. So we have alpha, beta, and gamma, and on the numerator we will have alpha beta plus gamma beta plus gamma alpha. And what about the negative sign? So we'll have a negative sign over here, and then yeah, that's it. So all of them will get positive numerator. So the sum of the roots taken 2 at a time is 4 by minus of minus 1, which is 4. So this is the value of this particular expression. Okay, so basically we have to see how easily, as much as possible, we should be able to solve it easily rather than complicating it with big simplifications, because it takes a lot of time in solving all those simplifications. Okay. Now next one is solving cubic equations. See, as such, there is no specific method to solve cubic equations. But what generally we do is, so suppose we have a cubic equation like x cube plus 2x square minus x minus 2 is equal to 0. Suppose this is a given cubic equation which I have. So there is no specific rule which we can use to solve this equation. But one thing which we generally use it, the first root we try to find out by observation, or you can say hit and trial method. In decent language, we can call it as by observation. So first root we try to find out by observation. So the possibilities which we can see is x is equal to 0 or 1 or minus 1 or minus 2 or 2. So generally one of these numbers will be one of the roots. And once we find out one root, then we can get the equation in the form of a quadratic and then try to get the other two roots. Okay, we can, just like we had learned in our 10th class, the polynomial division. So that we can use and then find the quadratic equation. So let's do this example. So in this case, if you see x is equal to 0 doesn't satisfy, because x is equal to 0 will not give me the value here. So if I take x is equal to 1, so this will become 1, this will be 2, this is minus 1, this is minus 2. So x is equal to 1 is one of the root of this particular equation. So I can do like this, x cube plus 2x square minus x minus 2. So I divide this with x minus 1, because x is equal to 1 is a root. So that's why I divide with x minus 1. So the first coefficient term I'll get is x square. So this will be x square minus x cube minus x square. So if I subtract, this will be gone. I will be having 3x square minus x minus 2. So again, let me have 3x here. So this will be 3x square minus 3x. Again subtract. So this will be plus. This will get cancelled. And I'll have 2x minus 2. And here I will have plus 2. So that I have here 2x minus 2. My remainder will be 0. So this cubic equation I can write as x minus 1 multiplied with x square plus 3x plus 2 is equal to 0. So we can simplify this x square plus 3x plus 2 is equal to 0. And then we get x plus 1, x plus 2 is equal to 0. So the given cubic equation will have x is equal to 1, minus 1 and minus 2 as the roots. So that's how we solve a cubic equation. So as I mentioned, there is no specific rule which we use to solve it, but we first have to find out one root by using observation. Generally, these are the roots which will be there. Sometimes it may be 3 also, but generally these will be the roots. I don't think so they will ask beyond 3 or minus 3. So we can try these one of the roots, and then using those roots we can try to find, we can divide and then find the coefficient. So that will be the quadratic equation. So the coefficient multiplied with that one root will give me the entire cubic equation. So again we solve that quadratic equation as we do by factor method or by any other method, and then we can get the factors, and that's how we resolve the given cubic equation into the factors. So the next finding range of a quadratic. So suppose we are given a quadratic function, so we need to find the range. So let's take an example. Okay. So he's asking us to find the least value of this rational expression. So this is a quadratic equation on the numerator, quadratic equation on the denominator. What is the least value of this particular expression? So when we have to find out the least value, first of all, we need an inequality. Now, whenever we say the least value or the greatest value, that means the value has to be less than equal to some other value, or it has to be greater than equal to some other value. Yes, so that's how we get the least value or the greatest value. So in this case, for least value, so this is the given expression. So one way of doing it is, let us assume it as y, and then get just simplify it a little bit by rearranging the terms. We can take this on the other side, we get 5y x square minus 18y x plus 17y. So now let's bring all the x terms, all the x square and x terms on one side. We'll get 6 minus 5y x square plus 18y minus 20x. This 18y I'm taking on this side, and here I'll have plus 21 minus 17y is equal to 0. So if we carefully observe, again this is a quadratic equation with these coefficients. Okay, because y is in the coefficient. So now this quadratic equation must have real roots. Then only we will have this quadratic expression exists. So for x to be real, we have the discriminant greater than equal to 0. So this is the inequality which we will use in this case. So when discriminant is greater than equal to 0, because this expression is true for all real values of x, so that's why we have discriminant is 18y minus 22. This is my b square minus 4a. A is my 6 minus 5y. C is 21 minus 17y is greater than equal to 0. So if you see, basically we'll end up in getting a quadratic in y. So this will be, okay, let me take 2 as common outside. So I'll have 9y minus 7 square. This is 4 outside minus 4, 6 minus 5y, 21 minus 17y greater than equal to 0. So this 4 and this 4 will get cancelled. So this will be 81y square plus 121 minus 198y minus, if I multiply this will be 6, 12, okay, let me put a bracket, and 6 17s are minus 102y. This will be minus 105y plus 85y square is greater than equal to 0. Okay, so then we will get 81y square plus 121 minus 198y minus 126 plus 207y minus 85y square greater than equal to 0. So now if we simplify it, we'll get minus 4y square. This is 81, this is minus 85, so minus 4y square. And then this is minus 198 and this is 207. So this will give me plus 9y, and this is 121 and minus 126. So this will be minus 5 is equal to 0. So let me this is greater than equal to 0. So let me multiply with minus 1 on both sides. This will be 4y square minus 9y plus 5 is less than equal to 0, because whenever we multiply with minus 1 on both sides, for inequality the sign gets reversed. So this will be 4y square minus 4y minus 5y plus 5 is less than equal to 0. So if we simplify, this will be 4y, y minus 1 minus 5, y minus 1 is less than equal to 0, which is 4y minus 5, y minus 1 is less than equal to 0. So if we recall from our beginning of inequality we had discussed, so whenever we have an inequality like this to solve, so first of all we have to put the points. So this is my 5 by 4. So 5 by 4 is greater, so put the greater point here, and the smaller one is 1. So put a positive sign over here, and then because the degree of this term is odd, so that's why the sign will get changed. And then again, the degree of this term is odd, so again the sign will get changed. So when my y is in this region, then the value is less than 0, and when my y is in this region, then it will be greater than 0. So for less than equal to 0, basically my y will belong to 1 to 5 by 4 closed. Okay, so this is where my y will belong. But what is my y? Y is this given expression. What he was asking us is the least value of this expression. So the least value of given expression is 1. So that's how we have to use the inequality and solve the equation. Okay, so let's do another question. Some problem. So find the domain and range of this given equation. So when I say f of x is equal to this, so I can also write it as y is equal to under root 3 minus 2x minus x square. So as we have already seen that whenever we are taking care of the domain, then we have to make sure that the term which are inside the square root are always greater than equal to 0. So for domain, let's use that simple condition, that is my 3 minus 2x minus x square should be greater than equal to 0. So if I multiply both sides with minus 1, I will get x square plus 2x minus 3 greater than equal to 0. So let us simplify it, and we get x square plus 3x minus x minus 3 greater than equal to 0. So this will be x minus 1 multiplied with x plus 3 greater than 0. Again, we use the same method. So this is minus 3 because x plus 3 I have. So that's why I put minus 3 here and 1. And here I will have, okay, 1 second. I think here. Because when we multiply with minus 1, sign gets reversed. Okay. So, yeah. So first we put plus sign here, and then because the degree is odd, we put a minus, and then again the degree is odd, we put a plus. So we need this particular expression has to be less than equal to 0. That means it has to lie in this interval. So my x should belong to minus 3 to 1 closed. So this will be my domain. And now if I want to find out the range, basically I want to find out the minimum and maximum value of this particular expression. So let's use this method, say 3 minus x square. So this can also be written as, say I can write as 3 plus 1 minus 1 minus 2x minus x square. So basically what I'm trying to do is I'm trying to convert this as one of the squares. So I will get 4 minus x plus 1 whole square. So why I'm doing like this is because I know that the minimum value of this particular term is 0. Yes, so because I know the minimum value of this, so I know the minimum value of the whole expression. So I can say that this y y has maximum value when x plus 1 is equal to 0. Okay, and what is that maximum value? It is under root of 4. So, and also this square root of something is always greater than 0. So my range I can write as y belongs to 0 to 2. Why I'm getting 2? Because here for maximum value of y I have 4 minus 0. This is when this term is 0, then this y will be maximum. So this is my 2. This is y max. Okay, so the y max is 2 and I'll have the minimum value of y as 0. So that's how my range I'll be getting as 0 to 2. So let's discuss the next thing, that is graphs of quadratic equation. So suppose I have a quadratic equation y is equal to ax square plus bx plus c. So I can rewrite it as y is equal to a multiplied with x square plus b by ax plus c by a. Let me take the a on the other side. This will be y by a is equal to x square plus b by ax. Now I'll try to convert this particular expression as a perfect square. So this will be 2 and divided by 2 plus b by 2a whole square minus b by 2a whole square plus c by a. Okay, so this is what I'm left with this side. This will be y by a is equal to x plus b by 2a whole square minus b square by 4a square plus c by a. So, okay, let me take these terms on the other side. What we will have is y plus b square by 4a square minus c by a is equal to x plus b by 2a whole square. So if I take LCM, I will get, okay, let me just write it as y minus a, y by a here, plus take LCM in these terms. So this will be 4a square, b square minus 4ac is equal to x plus b by 2a whole square. So this is what I have got. And I know that this term, that is b square minus 4ac, is nothing but d. So I can write it as y minus a, y by a plus d by 4a square is equal to x plus b by 2a whole square. If I take a on one, a on the other side, I will get y plus d by 4a is equal to a multiplied with x plus b by 2a whole square. So this is nothing but the equation of a parabola. When I have a equation of this form, y is equal to, say, some ax square. So this is an equation of a parabola which will be either like this or like this. If this is my x-axis, so then it will be either like this, like a u, or it could be like this also, or it will be upside down u. Okay, so this is how generally the graph of this parabola looks like. So now let's specifically draw the graph when a is equal to 0 and d is greater than 0. So this is my first case. So when A is greater than 0 and D is greater than 0, I will have graph like this. So that basically means it will have real roots, two distinct roots, and A is positive. When A is positive, it is a U, and when A is negative, then this is upside down U. This is for A less than 0, and this is A greater than 0. Okay, so this is my first case. Let's take the second case. A is greater than 0 and D is equal to 0. So in that case, I will have one root, equal root. So it will just touch it. This is the one root. As we have seen, root means nothing but the point where the graph touches the x-axis. This is my x-axis, this is my x-axis. So this will touch at only one point. Now in third case, I have A greater than 0 and D less than 0. So in this case, the graph won't touch the x-axis. That means that's why we don't have any real root. We have only imaginary roots. Now let's take the fourth case. And A is negative and D is greater than 0. So in that case, again, we have real roots, but the graph will be upside down. Okay, and then if we have A less than 0 and D is equal to 0, again, the graph will be upside down, but will have only one root. Fine. And the last case, when A is less than 0 and D is less than 0, the graph will be upside down U and won't touch the x-axis. So that's how we can understand the graph of this particular quadratic equation will look like. It will depend on the sign of the A and it will depend on the discriminant. Okay. Location of roots. So sometimes we want the roots of a given quadratic equation. Say suppose we have ax square plus bx plus c is equal to 0 is a quadratic equation. And alpha, beta are the roots of this equation. So we want the roots of the equation to be in a particular interval. So for that, we put some restriction on A, B, and C. We put some condition on A, B, and C, and then accordingly manage to get alpha, beta in a particular interval. So based on which interval alpha, beta are lying, or how exactly alpha, beta are lying, we have different cases. So let's take first case. So suppose we have alpha, beta, both positive. Now here I'm assuming that alpha is less than beta. Okay. So alpha, beta, both are positive. That means I will have, say this is my alpha, this is my beta. Both are positive. That means my origin will be here and both are on positive side. Otherwise, another option will be like this. My origin is here and this is beta. So what are the conditions for alpha beta to lie on the positive side of the x-axis is basically my discriminant should be first of all greater than equal to 0. So this is the first condition. My second condition will be the sum of the roots. In this case, if you see, because alpha and beta both are positive, the sum of roots will be greater than 0. That also will be positive. And my product of roots will be also positive because both alpha and beta are positive. So these are the three conditions which we need to check for alpha beta being greater than 0. So one way is that we check these three conditions. There is another way, or instead of checking these three conditions, or we can just check, of course, the first condition we check as it is, that is discriminant should be greater than equal to 0. Only then we'll be sure that we have two roots. And the second condition which we need to check is, if you observe carefully, if my, see, this is the graph when A is greater than 0, and this is the graph when A is less than 0. So when A is greater than 0, my f of 0 is positive. And when A is less than 0, my f of 0 is negative. So when this is positive, then this is f of 0 is also positive, and when this is negative, then f of 0 is also negative. So can I write a multiplied with f of 0 is always greater than 0? So whether depending on a being positive or negative, my f of 0 is also positive or negative, such that the product is always positive. So this is the second condition. And third condition will be, we have seen that this is my minus b by 2a. So this is the graph, this is the point where I'll have, this is the value of x for which I will have the maximum, that is minus b by 2a. So for that value of x, I will have the maximum or minimum of that particular quadratic equation. So similarly here also, this point will be my minus b by 2a. So in both these cases, my minus b by 2a is always positive. Okay. So we can either check these three conditions, that is discriminant greater than equal to 0, sum of the roots positive, product of the roots positive, or we can just check the discriminant is greater than 0, a multiplied with f of 0 is greater than 0, and the point where it is either maximum or minimum, that is greater than 0, or that is positive. So this is the first case where my both roots are positive. Now let's take second case where alpha, beta are both negative. So in that case, I will have 0 here. One way, or this is another way. Fine. So yeah, here I have alpha, beta, because we have taken alpha is less than beta. So again here it is alpha, beta. So again in this case also we have my discriminant should be greater than 0, greater than equal to 0, and the second condition will be sum of roots are negative because both are lying on the negative side, and product of roots will be positive because both are negative. Negative multiplied with negative will be positive. That's how I'll be getting product of the roots greater than 0. So these three conditions can be checked, or we can check just discriminant greater than 0 is the first condition. And if you see here, this is my minus b by 2a, the peak, and here this is minus b by 2a. So again here minus b by 2a in both the cases will be less than 0. And if you see, if this is the case when a is less than 0, and this is when a is greater than 0. When a is less than 0, my f of 0 is also negative. When a is greater than 0, again my f of 0 is positive. So the condition will remain same. That is a multiplied with f of 0 is positive. So we can check either these three conditions, this and this and this, or this and this and this. Okay. So all these three conditions, or all these three conditions have to be checked. And the third case is when one root is less than 0 and other root is greater than 0. So that basically means this is my alpha, this is my beta, and this is 0. It could be like this or like this. Okay. So in this case, the very fact that we have 0 lying in between two roots, that itself says that my discriminant will be greater than equal to 0, that because I'm having two distinct roots. Yes. So this condition is already satisfied. I need not check that. And some of the roots, I can't say anything. But only thing I can say something is about the product of the roots. That is, the product of the roots has to be negative. So that is one condition I can use. That is, product of roots has to be less than 0. Or another condition I can use is, if f of 0, okay, this is when a is positive and this is when a is negative. When a is positive, my f of 0 is less than 0. When a is negative, my f of 0 is positive. So basically, my a multiplied with f of 0 is less than 0 in this case. So we have only one condition to check. Either we check the product of the roots should be negative, or otherwise we check that the, the product of a multiplied with f of 0 should be less than 0. So either of these two conditions we can check. So now let's take the next case, that is alpha, beta, both are greater than a constant k. We have both the roots which are the first case we had seen, both the roots are greater than 0. Now we are saying both the roots are greater than a constant k. So again, it will be similar case. So my k in the previous case it was 0, but here I'm taking a general term. So this is k. So this is k. Obviously, I can also have like this. This is k, and I have one root over here. It's touching at one point. So that is also possible, provided alpha and beta both are same. And this is another possibility where it is touching at only one point. Okay. So what are the different conditions which I'll have to check in this case is, the first one, my discriminant should be greater than equal to 0. Yes, when it is greater, then I'll have this condition. When it is equal, then I'll have this condition. This is when a is greater than 0, and this is when a is less than 0. This is when discriminant is greater than 0. This is when discriminant is equal to 0. The same thing over here. Okay, so this is the first condition which I need to check. Okay, when my f of k, when my a is greater than 0, then f of k is positive. And when a is less than 0, f of k is negative. So then again I can apply this rule. A multiplied with f of k is always positive. So this is the second condition which I need to check. And the third one is very similar to what we had done previously. This is minus b by 2a. In this case also this is minus b by 2a, and here also this minus b by 2a, minus b by 2a. So minus b by 2a is always greater than k. So it's nothing but the previous case we had 0, that 0 we are replacing here with k. It's exactly same. So this is my fourth condition, and now we have the fifth condition, when alpha, beta both are less than k. So again I have this is my alpha, beta, this is k, or it will be like this. This is alpha and beta. Again, this is when discriminant is greater than 0, and when it is equal to 0, I'll have touching at one point like this. And this is k. Okay. So in this case, again, the conditions are similar. The first condition which I need to check is my discriminant should be greater than equal to 0. The second condition which I need to check is when my a is negative, my f of k is negative. When a is positive, then f of k is positive. So the product of a and f of k is always positive. And the third condition is minus b by 2a. This is my minus b by 2a. So in all the cases, minus b by 2a is less than k. Okay. So this is the third condition. So we have to check all the three conditions. It's not that any one of them, but we have to check this and this and this here also and. Fine. So now let's take the next case. It is case 6. When k is in between the roots. So I will have like this. This is k, this is alpha, this is beta. Another case will be this is alpha, this is beta, this is k somewhere in between. So in this particular thing, I just need to check one thing, because the very fact that alpha, beta are the two roots, that means my discriminant has to be greater than equal to 0. So no need to check on that. Only thing I need to check is when my A is positive, my f of k is negative. And when A is negative, f of k is positive. So the product of A and f of k is always negative. So this is the only condition which I need to check, and that would be sufficient for me to get the desired thing. Okay, so these were the 6 cases. Now let's go to the next case. So we have exactly one root lying in K1, K2. So this is the interval K1, K2. So we have exactly one root which is lying between this interval. So basically it will be something like this. This is my K1, this is my K2, because K1 is smaller, so I'm writing K1 over here. Or otherwise it will be like this, K1, K2. Okay, so we have exactly one root. Okay, so it could be also like this. Here is my K1 and here is my K2, or otherwise here is my K1, here is my K2. So these are the different conditions which are possible. So in all these cases, we see that when f of K1 is positive, f of K2 is negative. And when f of K1 here is negative, f of K2 is positive. Here f of K1 is negative, f of K2 is positive. So f of K1 and f of K2 are always of opposite sign. So if I take the product, that will be always less than 0. So this one condition is sufficient for me to check. And because now the exactly one root is lying between K1 and K2, that itself means that it will have more than one root. So discriminant need not be checked specifically. So we have the next case, the 8th case is when both roots lying in the interval K1, K2. So what happens here is we have this. So both the roots are lying in this interval. So this is my K1, this is my K2. So both alpha, beta will lie in this interval. So this is one case, or this is K1, this is K2. Again, alpha, beta. So these are the cases which I will have when both the roots are lying in this interval. Obviously, if I have a common root, then it will be like this. In this case, it will be like this. It's K1 and this is K2. Okay, so this is the case when my A is greater than 0, and this is the case when A is less than 0. And this is the case when discriminant is greater than 0. And this is when discriminant is equal to 0. So from these graphs, we can see that when A is positive, f of K1 is positive and f of K2 is also positive. When A is negative, f of K1 is negative and f of K2 is also negative. So basically I can write the first condition as A multiplied with f of K1 is positive and A multiplied with f of K2 is also positive. So these two conditions has to be satisfied. Now the second condition which I need to check is, this is my minus b by 2a. So in all the cases, we see that minus b by 2a will be between K1 and K2. Okay. So whatever case, whatever we take, whether A is greater than 0 or less than 0, or discriminant is greater than 0 or equal to 0, we will always have minus b by 2a lying between K1 and K2. and the third condition will be my discriminant greater than equal to 0. Because only when discriminant is greater than equal to 0, I'm sure that I will have two roots. Otherwise, there is a possibility of like this also. K1, K2 are here and it is not touching. Yes. So that to avoid this case, we are taking discriminant is greater than equal to 0. Okay. In the previous case, in fact, you can check yourself that the very fact that we take this condition, that itself means that discriminant will be greater than equal to 0. That will, while solving it, you will in between come across a condition where discriminant will be greater than equal to 0. So that's why we are not checking the discriminant in this particular case, the previous case. Okay. But here we will have to check that. Okay. So the last case, that is case 9, is, so this was both the roots lying between K1 and K2. Now we have one root is smaller than K1 and other root is greater than K2. So in this case, how will it look like? So this is my K1, one root is, no, sorry. One root is smaller than K1, the root is greater than K2, or it will be like this. So basically my K1, K2 will be in between the roots. So this is when A is positive, this is when A is negative. So in this case, when A is greater than 0, my f of K1 is negative and f of K2 is also negative. And when A is less than 0, f of K1 is positive and f of K2 is negative, is also positive. So what I need to just check is A f of K1 is less than 0 because they are of opposite sign, and A f of K2 is less than 0. So both this less than 0 needs to be checked. If this is checked, then a problem will be solved. Just recap what all conditions or what are the different cases we discussed. So for the location of roots, we have this quadratic equation ax square plus bx plus c is equal to 0. Alpha, beta are the roots. So when we want the roots to be in a particular interval, so we apply some conditions on the coefficients a, b, c, and then accordingly we can put the roots in a particular interval. So when the first case was when we want both the roots greater than 0. That means we want them to be in the interval 0 to infinity. So in that case, we have to have either a discriminant greater than 0 and sum of the roots should be positive and product of the roots should be positive, because both the roots are lying on the positive side. So that's why the sum should be positive and the product should be positive. So we need to check all these three conditions, or otherwise we need to just check discriminant greater than equal to 0. The product of A and f of 0 should be greater than 0, and minus b by 2a should be greater than 0. So either these three conditions or these three conditions, any of these three conditions we can check and proceed. So similarly, we have when both the roots are negative, we have similar conditions. But here the sum remains negative, the product, the sum becomes negative and the product remains greater than 0. And minus b by 2a will become negative and the product of a and f of 0 will. So now the next condition was when one root is negative, other root is positive. So in that case, we can't say anything about the sum because it will depend on the magnitude or the distance of alpha from 0 and the distance of beta from 0. As such, we can't explicitly say anything about the sum. But one thing we can say is about the product, that the product of the roots will be negative because one of them is negative, other is positive. So the product will be overall negative. Or otherwise, we can say that when A is positive, f of 0 is negative, and when A is negative, f of 0 is positive. So the product of A and f of 0 will be negative. So now that 0 we are replacing with some constant k. So for any number k, we can have similar conditions. But here the three conditions will be my discriminant greater than equal to 0, the product of a and f of k will be positive, and minus b by 2a will be greater than k. Similarly, when both the roots are less than k, then I will have these three conditions. And when the roots are one root is less than k and another root is greater than k, then I have only one condition. See, whenever 0 is lying between the roots or k is lying between the roots, then I have only one condition. That is, the product of a and the f of k or f of 0 is less than 0. Next condition, next thing was when we have exactly one root lying between k1 and k2. So k1 and k2 are two constants and we have exactly one root. So we have these four conditions. So here we need not check the discriminant thing, because while we are solving this, the discriminant will be included. The condition for discriminant to exist will already be included in this particular equation, inequality. So f of k1 multiplied with f of k2 is less than 0. So that's what one thing we need to check. And then when both roots lying in the interval, so the roots are between k1 and k2, so we have these conditions depending on a and d. So for that we have these three conditions, that the product of a and f of k1 should be positive, and similarly a and f of k2 should be positive, and minus b by 2a should be between k1 and k2, and the discriminant should be greater than equal to 0. And the last case was when one root is smaller than k1 and other root was greater than k2. So in that case, we have k1 and k2 both lying between the roots. So we have these two conditions. That is, a f of k1 should be less than 0 and a f of k2 should be less than 0. So that's how these are the different cases which we will have to use. So let's do this question. Let's make it a little bigger. Yeah, so it has a lot of bits, and by solving this one question, our location of roots concept should get clear. Okay, so he has given a quadratic equation and he's saying this is the quadratic equation. Find the values of m for which the roots. So he's asking us to find the values of m for which he's putting restriction on the roots. So the roots has to be real and distinct. Let's take the first bit. So roots are real and distinct. So when I say real and distinct, my condition is discriminant has to be greater than 0, not equal, because when I say equal, that means it has equal roots. So for real and distinct, my discriminant has to be greater than 0. So what is my discriminant? This is minus b by my b square minus 4ac. So this is m minus 3 square. This is my b square minus 4. A is 1 and C is m. So this is greater than 0. So that will give me m square plus 9 minus 6m minus 4m is greater than 0, which implies m square minus 10m plus 9 is greater than 0. That is m minus 9, m minus 1 is greater than 0. Again, we can use our plus minus plus. This is my 9, this is 1, this is plus, this is minus, and this is plus. Okay, so I need greater than 0. That means my m will belong to minus infinity to 1, open interval, because it is only greater than union 9 to infinity. So this is my first bit. My m will belong to this interval. Now if I want equal to 0, the second bit, my discriminant will be equal to 0 for equal roots. Okay, so for that, the equations will be exactly same. Only thing I'll get m square minus 10m plus 9 is equal to 0, which will give me m minus 9 multiplied with m minus 1 is equal to 0. That is m is equal to 1 and 9. Okay, so these will be the values of m. So now when when the roots are not real, that means the third condition will be discriminant less than 0. That is non-real roots. So for that, again, my equations will remain same. Only thing, the condition will get changed to less than 0. And my m, in this case, I have to consider the interval where it is negative sign. So it will be between 1 and 9. Again, here also open interval because it is only less than 0. So now let's take the fourth bit. They are of opposite sign. So the roots are of opposite sign. So that means it will be like this or like this. That means 0 is in between and one root is less than 0, another root is greater than 0. So that basically means we have seen the condition which we need to check is product of roots is less than 0. Yes. So my product of the roots with this will be m. So m has to be less than 0. So the given expression is x square minus m minus 3x plus m is equal to 0. This is the given quadratic equation. So for this, the product of the roots to be less than 0, my m has to be less than 0. Simple. So this is the interval for which the opposite sign. Now next is they have equal in magnitude but opposite in sign. So what it means is, so this is the origin. This is the roots. Of course, I didn't come properly, but if this is alpha, okay, if this is alpha, this is minus alpha. So both roots are equal in magnitude, but opposites in sign. Okay, so that means they're equidistant from the origin. So in that case, clearly we can see that alpha minus alpha, that is sum of the roots, is equal to 0. So what we have to take in this case is the sum of the roots, that is minus b by a. Minus b by a will be minus of minus m minus 3 will be equal to 0, which is m is equal to 3. So when my m becomes equal to 3, then this will be having roots equal in magnitude but opposite in sign. Now the next one is when both the roots are positive. So when we need both the roots positive, that means it will be either like this is my 0, or it will be like this. Yes, or it could be also like this. This is orange. Right. So both roots are greater than, both roots are positive. Yes. So the conditions which I need to check in these cases is discriminant should be greater than equal to 0, and the product of a multiplied with f of 0 should be greater than 0, and minus b by 2a should be greater than 0. So either I can check these three conditions, or I can check discriminant greater than equal to 0 and sum of the roots positive and product of the roots positive. So here, because the sum and product are readily available for me in the equation, so I can use that. So first let me take discriminant greater than equal to 0. For discriminant greater than 0, again I'll get the same equation, x minus 9, x minus 1 is greater than equal to 0. So this x minus 9, x minus 1, sorry, m minus 9, m minus 1 we have got from here. So this will be m minus 9, m minus 1 greater than equal to 0. So that means, again, this is 1, this is 9, plus, minus, plus. So m belongs to minus infinity to 1. In this case, I'll have closed because it is greater than equal to union 9 to infinity. So this is where my m has to lie, and also my sum has to be greater than 0. That means my sum of roots is m minus 3, So m minus 3 should be positive. That is, m should be greater than 3. Okay. And also, so this is one condition, first condition, this is second condition, and my products should be positive. That means the product of the roots is m, so that has to be positive. So if I take intersection of all these three, basically I will get m belongs to 9 to infinity. This is closed and this is open. So when m is lying in this interval, then it will satisfy this condition, this condition, this condition. Okay, so that is when my all roots are positive, all the roots are positive. Now when, so let's take the next bit, that is seventh one, when both the roots are negative. So in that case, this is 7th, both roots are negative. So alpha, beta are both less than 0. So in that case, I will have discriminant less than, discriminant will be greater than equal to 0. This is first condition. The second condition is because both the roots are negative, I will have sum of the roots will be less than 0 and product of the roots will be greater than 0, because both roots are negative. When we take product, it will be greater than 0. So the conditions will remain similar except for the sum of the roots. So this will give me m belongs to minus infinity to 1 union 9 to infinity, as we have got here. And sum of the roots less than 0, that will give us m minus 3 will be less than 0, which is m is less than 3. And product of the roots greater than 0 will be as it is. So if we try to see where exactly is this lying, this is a 0, this is 1, this is 3, this is 9. Okay, I'm just drawing it approximately. So my m has to lie less than 1 or greater than 9 is the first condition. Then my m has to be less than 3. So this is the second one. And m has to be greater than 0. So this is my third one. So if we take the intersection, so this is the region which is satisfied by all the three. So basically my m will belong to 0 to 1. And 1 I have closed and open at 0, because here it is greater than 0. It cannot be 0. Fine. So this is my condition when both the roots are negative. The next one is at least one root is positive. So when I say the eighth one, at least one root is positive implies either both roots are positive or exactly one root is positive. So when I say at least one root has to be positive, that means either both the roots are positive or exactly one root is positive. So both the roots are positive. So what is the condition? I think this we have already solved. The sixth one, that is both the roots are positive. So that is my m is from 9 to infinity. So this is m belongs to 9 to infinity. And okay, this will, yeah, or exactly one root positive. For exactly one root positive, this will be opposite sign. Yeah. So this will be my this case. When one root is negative, another root is positive. So that is m less than 0. And m is less than 0. Fine. So this will give me 9, m has to be greater than 9 and it has to be less than 0. So amazingly, we will not Yeah, so it will be OR here. So this is the condition when both the roots are positive, and this is the condition when exactly one root is positive. So my M will belong to minus infinity to 0. This is open, union, 9 to infinity. Okay. So the next bit is both the roots are greater than 2. Both roots are greater than 2. So this is my 2. It will be like this, or otherwise like this, or like this. Fine. So when both the roots are greater than 2, the conditions which I'll have to use is f of 2 is a into f of 2, that is a in this case is 1, is greater than 0, and minus b by 2a, that will be, okay, right, minus b by 2a will be greater than equal to greater than 2, and the third condition will be discriminant greater than equal to 0. Fine. So f of 2, you just take the equation x square minus m minus 3 x plus m. So the equation is x square minus m minus 3 x plus m is equal to 0. So f of 2 will be 4 minus 2m minus 3 plus m is greater than 0, which implies this will be 6, 10 minus m is greater than 0, which implies m is less than 10. Okay. And so this is my first condition. Another condition will be minus b by 2a. So my m minus 3 by 2, this is minus b by 2a, will be greater than 2, which implies m is greater than, this will be 4 plus 3, 7. So m has to be greater than 7. This is the second condition. And my third condition will be discriminant greater than equal to 0, which implies m belongs to minus infinity to 1 union 9 to infinity. So if we take intersection of all these three conditions, we will get m will belong to, it has to be less than, let's draw this, this is 7, this is 9, this is 10, and this is 1. So it has to be less than 10, and it has to be greater than 7. It has to be either here or here. So the intersection will be this. So my m will belong to 9 closed, 10 open. So 9 to 10. Fine. So this is when both the roots are greater than 2. The next case is both the roots. Okay, this was when both the roots are greater than 2. That was 10th condition. I have written 9, so that is put as 10th. 9th one was one root is smaller than 2 and other root is greater than 2. Okay, it's again simple. So this is my 2. So one root is smaller than 2, another root is greater than 2, either this or this. So whenever it is in between, we know the condition is a f of 2 will be less than 0. This is when a is greater than 0. This is when a is less than 0. So a is 1. So my f of 2 has to be less than 0. So f of 2 will be, just put 2 instead of this. So this will be 10 minus m less than 0. which implies m has to be greater than 10. So this is the condition when my this is 2 is between the roots. Okay, so then let's take the next one. Both the roots are smaller than 2. Okay, let's do that also. 11th one, 10th we have already done. So both the roots smaller than 2. So this is my alpha, beta, this is my 2. Fine. So in this case, the conditions which we'll have to consider is discriminant greater than equal to 0, minus b by 2a will be less than 2, and then a f of 2 will be greater than 0. Fine. These were the 3 conditions. Again, you can check from the theory what we had discussed. You will get these 3 conditions. So if we apply these conditions in the given equation, we will get m belongs to minus infinity to 1 union 9 to infinity, and here I will have m belongs to when it is less than 2. For greater than 2 we got this, for less than 2 we'll have m will be less than 7. Okay, and when this is greater than 0, then I will have 10 minus m greater than 0, which implies m will be less than 10. So ultimately, the interval which I will have will be, this is 1, this is 7, this is 9, this is 10. So it will go like this, This is the first one. It has to be less than 7. So that means here, and it has to be greater than 10. So that is here. Oh, it has to be less than 10. So it will be here. So if we want to take the intersection of all this, then it will be nothing but this region. So minus infinity to 1. This will be closed. Okay. So that is my 11th one, minus infinity to 1. So let's see the next bit. The next bit, the 12th one, is exactly 1 root lies in 1, 2. Okay, so the equation is x square minus 3x plus m is equal to 0. So this should have exactly 1 root lying in this particular interval. So this is my 1, 2. So it will be either like this or like this or like this, like this. So either of these 4 conditions we will have. So when exactly 1 root has to lie between this, the conditions which I need to use is, of course, discriminant need not be checked. Only thing I need to check is here that a f of 1, when my a is greater than 0, f of 1 is less than 0. And when a is, and f of 2 is greater than 0. Okay, so the condition here is f of 1 and f of 2 both are always of opposite sign. So it will be f of 1, f of 2. The product is negative. So f of 1 is what? 1 minus m minus 3 x plus m, which is my f of 1, and f of 2 is 4 minus 2 m minus 3 plus m is less than 0. So if I write it a little properly, this minus m and plus m will go away, and here I'll have 4 multiplied with, this will be 4 plus 6. So this is 10 minus 2m plus m. So this will be minus m less than 0. So that basically means 10 is less than m. So for exactly one root to lie between 1 and 2, I should have my m belongs to 10 to infinity, open interval on both sides. Okay, so the next bit was 13. Both roots lie in the interval 1 and 2. It's like this or like this. So both the roots are lying in this interval. Obviously, it could be like one root also, a common root. So for that case, the conditions which we'll have to consider in this will be my discriminant has to be greater than equal to 0, and my a f of 1 should be positive, and a f of 2 has to be positive, and apart from that I should have my minus b by 2a should lie between 1 and 2. So these are the three conditions which I need to check. So let's do it one by one. So for this, I will have m belongs to minus infinity to 1. This we have already done. 9 to infinity. For this, it will be, I think for this we had, okay. So if we put m x is equal to 1, we will get the equation is x square minus m minus 3 x plus m is equal to 0. So a is 1. So f of 1 is greater than 0 implies 1 minus m plus 3 plus m is equal to 0. So this goes with this. We are getting 4 is equal to 0, which is never true. So this won't happen anytime. Yes. So this condition will never happen. Yes. And then if I take f of 2, in fact, I need not check also other conditions, because when this condition will never satisfy, that itself means that whatever other conditions satisfy or not, I will not have any m, because there is no m existing such that this particular condition satisfies. So in fact, I need not check further any more conditions. I can just write m belongs to 5, or it's a null set. Yes, so that, then take the next bit, that is 14th. So there he says exactly one root lies in, no, I think at least one root lies in 1 and 2. So this is at least one root lies in 1 and 2. So again, when I say at least one root lies in 1 and 2, it implies exactly one root or two roots in 1 and 2. So it means it should have exactly one root lying in 1 and 2, or it should have both the roots lying in 1 and 2. I think these we have already solved before. For exactly one root, we have the 12th one, and both the roots we have 13th one. So when we say at least one root lies in the interval, so that's the combination of 12th and 13th. So that we can we can just take union of both of them. The last one is, so okay, let me write it here. So 14th question is nothing but 12th answer union 13th answer. Okay. One root is greater than 2 and other root is smaller than 1. So that basically means this is 15th. So one root is greater than 2. This is 1 and 2. The other root is smaller than 1. So this is how it will lie. Fine. So it will be either like this or like this, where one root is either greater than 2 and other root is smaller than 2. So in this case, the condition is very similar. Very simple. We have to just check a f of 1 is less than 0 and a f of 2 is less than 0. So for the first one, we will have f of 1 will be 4. F of 1 will give me 4, which is less than 0. Again, this is not possible. And then for the second condition, it will be, we have done this before. Yeah, f of 2 here, 10 minus m. So f of 2 is equal to 10 minus m is less than 0, 10 less than 2. So here it's not possible, and here it is less than 10. So because one of the condition is not possible, that's why m belongs to null. No such m will exist. So this is how we approach the questions of location of the roots. So we have to understand the conditions which we are applying, and then accordingly, depending on the question which is given, we have to accordingly use the conditions and get the values of m in this particular case, or the relation between ABC coefficients. Okay, so thank you.